And welcome back, Night Owls. This is Dr. Nighttime, and tonight we're going over standard deviation and why we specifically use standard deviation in our calculations. Now, you might think, alright, why, of course we know why we use standard deviation, right? We use it as a measure of how far away our data are from their average value, right? But that's not what I mean. What I mean by this is, why do we do this complicated procedure with the squaring and summing and the square root, right? Why not just do a simpler procedure of just measuring the difference between your actual values and your average value, measuring how far apart those are, and just averaging them. No squaring, no square rooting. Wouldn't that be easier? And the answer, yes, it would be easier. But there are other considerations. So, definition of standard deviation is it's the square root of the sum of square differences from the mean, all averaged, right? So you take your average square distance from your mean, that's called your variance. Variance is the average square distance from the mean, and you take the square root of that. Why not just use absolute values, right? Instead of squaring and square rooting, couldn't you use... So I'm going to use the symbol delta for mean absolute deviation of the mean. That's what this is called. So delta for just regular deviation. And that would be just the sum of the absolute values of the distances from the mean, all divided by the total number, right? So you're just taking an average, or averaging your differences from the mean. Now, doing that would be a measure of spread. It would be a measure of how far away, how far apart your data were likely to be from each other. However, it's not the standard that we use. And over the course of this video, I'll discuss why we use a different standard and what it's good for. Obviously, so absolute values have their obvious upsides, right? This mean absolute deviation, right, has its obvious upside. It's easier to calculate. Squaring a bunch of numbers is difficult. Taking a square root by hand is even more difficult. Whereas we don't have to do any of that, we're just adding and dividing with absolute values, and with the mean absolute deviation of the mean. And the key to why we do this is it deals with independent sources of randomness, and how you can measure independent sources of randomness. Let's start with and we'll go through a standard coin flipping example, right? So you flip a coin a bunch of times, each time it either comes up heads or tails. If you flip a coin 0 times, clearly you're always going to get 0 heads, right? We want to count the number of heads and try to get the standard deviation, or these different deviations of numbers of heads. Obviously, you're 100% guaranteed to get 0 heads when you flip 0 coins. So that's going to mean that both your standard deviation sigma is 0 and your mean absolute deviation delta is 0. Both of them are 0. Not too difficult there, right? If there is no uncertainty, there is no deviation no matter how you measure it. For one coin, the average is always going to be half a head, right? But it'll either be 0 heads or 1 head. In either case, you deviate from the mean by 1/2. That means any realistic measure of your deviation from the mean should give you a 1/2, because no matter what, you are always 1/2 away from your mean. So if your measure of deviation from the mean doesn't tell you 1/2, there's something funny about that. So obviously, sigma is going to be a 1/2 and delta is going to be a 1/2. 2 coins is where we actually have to start doing some math here. So if you flip 2 coins, the x, let x be the number of heads. X will either be 0, 1, or 2. 25% chance of getting 0, right? Tail followed by a tail. 25% chance of getting heads, head followed by a head, of getting 2 heads, head followed by a head. 50% chance of getting exactly 1 head, either a head then tail or a tail then head. And we look at the table here, we keep track of what x, the observed number of heads, minus the average number of heads would be. Obviously the average number of heads is 1, right? Flip a coin twice, on average it'll come up heads once out of those 2 times. Absolute values, so we keep track of the actual deviation, absolute value of the deviation from the mean, and the square of the deviation from the mean. When we average those together by comparing to the probabilities here, then for these two coins, we get sigma equals 1 over square root of 2, and delta equals a half. Okay. Notice that sigma is larger than delta. That'll consistently be true, just because as you miss by more and more, the squaring counts more. So further distances are kind of overweighted that way with sigma. When you do 3 coins, here are the possible numbers of heads, obviously 0, 1, 2, or 3. With Pascal's triangle or binomial theorem or any other way, or just flat out counting, you get a 1/8 chance of getting each of 0 or 3 heads, 3/8 chance of getting either 1 or 2 heads. We tabulate the deviations from the mean, absolute deviation from the mean, and square deviations from the mean. You can pause the video now if you want to just double check, make sure that these are the correct numbers. But then when you weight these all by probabilities, when you do absolute deviation from the mean, you'll on average get 3 out of 4. When you do square root of the mean square deviation from the mean, so you just weight these numbers right here and then take the square root of that, you'll get square root of 3 all over 2. So again, in this case, delta is like 0.75, and delta is 0.75, sigma is 0.8. At like 0.86 something. Yeah. And what about 4 coins? And trust me, this is as far as I'm going to go with this. 4 coins is the most complicated case I'm going to do here. Don't worry. This is the last of these tables you'll have to stare at. So we can get either 0, 1, 2, 3, or 4 coins. It's 0, 1, 2, 3, or 4 heads. The probabilities are 1/16 for each of 0 or 4, 1/4 for each of 1 or 3, and 3/8 for 2 exactly. We take we look at the actual deviations from the mean, take their absolute values, 2, 1, 0, 1, 2. Square deviations will be 4, 1, 0, 1, 4. Right? We weight those by the probabilities, crunch the numbers, and we get for the absolute deviations, we get 3/4 again. Notice it didn't change between 3 and 4. Also, if you look back, it didn't change between 1 and 2 either. And sigma gets us a 1, right, when you're done doing all the math here. And so let's tabulate these results all together. As n, our number of coins, increases from 0 to 1 to 2 to 3 to 4. Let's look at what delta is doing. Delta starts at 0, then goes up to 1/2, then stays at 1/2, right? Even though we added an additional coin, we're adding some uncertainty. But our measure of uncertainty, our measure of spread, didn't change, even though we flipped an additional coin. Our numbers are getting more spread out. It's not showing up here. Then it does increase again to go from 2 to 3, then not from 3 to 4. So what's happening here? Suppose that I've flipped some number of coins and that the number of heads and number of tails do not exactly match. So I either have more heads than tails or more tails than heads. When obviously the average case would be to have the same number. When I flip one additional coin, I'm either going to be making the imbalance 1 coin worse, right? If I had more heads than tails and I get another head, then I'm making it worse. Or I'll get it one coin better. So either 1 coin out of balance or 1 coin further into balance. And those will happen with equal probability. So unless I happen to start out exactly balanced, I'm consistently going to maintain, the additional uncertainty of 1 additional coin is not going to affect the average deviation. The one exception, of course, is if I start, before flipping that additional coin, if I start with the same number of heads and tails. That can only happen if I flipped an even number of coins. So that's why it kind of jumps up, then holds steady, then jumps up and holds steady. And that's kind of weird. We don't like functions that do that. Sigma itself has this kind of weird progression that has square roots in it, but take a look at sigma squared, the variance, the square of sigma. That actually has a perfectly linear progression, 0 to 1/4 to 1/2 to 3/4 to 1. What we get from this is that if I have two independent sources of randomness, the variance of one of them, so if I have the variance of one of them and the variance of the other, if I then sum those two, if I have another random variable that's just the sum of my two independent random variables, the variance of the independent sum is the sum of the individual variances. And what this means is that if you want to do math with your figures of spread and your figures of uncertainty, suppose I have one random variable and I've already calculated that it has this average and this variance. And I take another random variable and some other average and some other variance. Right? Now, assuming that they're independent, if I want to add them up, right, which you want to do a lot. You often in statistics, you have a whole bunch of different things that can influence something to go one way or the other, and you want to consider all those factors and add them up, and you initially presume they're independent. Or you could presume some specific correlation between them, in which case the variance formula is a little more complicated, but not nauseatingly more complicated. I won't talk about that here. But in the simple case where it's independent, you can simply say, as long as I know the mean and variance of one random variable and the mean and variance of the next random variable and the mean and variance of the next random variable, I can get the mean, right? So the mean is obviously the mean of the sum and sum of the means. If I just know the individual variances, then the variance of an independent sum is the sum of the individual variances, and that will always be true. Now, why do we use standard deviation rather than variance? That's purely to get the dimensions to work out the way we want them to. So, for example, if I were measuring things, suppose I were measuring lengths in meters, right? Then I would want to know, on average, how many meters off, typically, well, what's a typical deviation in meters? Well, when I take my difference of meters, and then I square that for variance, because in variance I'm squaring differences, that would get me something in meters squared. And so if typically my differences between two measurements were on the order of magnitude of 100 meters, then when I square that, I get something on the order of magnitude of around 10,000. And so that's why, mentally you want to take the square root of that just to give it a measurement you can actually compare to what you found. And so that's why, the other thing is, if you then take do a change in coordinate, or a change of variable, right, then your multiplication factor should scale linearly. So that's why we use standard deviation rather than variance. But this is also why we use variance rather than mean absolute deviation. Also, when you get later on, when you start doing calculus with this, you'll find that squaring is easier to work with than absolute values. When you try, but that's another matter. Just a simple case, simple explanation. We use standard deviation rather than mean absolute deviation because of this fact that variances of sums of independent random variables just get you the sum of the individual variances. Anyway, if you like the way I explain things and want to arrange private lessons, click the link in the description below. And as always, until next time, this is Dr. Nighttime wishing you a good night.